Marmaduke. You animal, you. Oh, hey there. I'm Moreno. Oftentimes in this modern day, we take things we see and do every day for granted. We don't really question why they should work. When something moves, we just view it as moving, just because it is. When you actually talk about the physics of motion, something that is essential to talk about are Newton's laws of motion. That's right, Newton. But who exactly is Isaac Newton? Sir Isaac Newton was born on December 25th, 1642, Christmas Day. Newton was educated at the King's School in Lincolnshire, England from the age of 12 to 17. He entered Trinity College, Cambridge University, in 1661. The funny thing is, he showed no exceptional ability during his college years, and graduated in 1665 without any particular distinction. He returned to Cambridge as a fellow lecturer in 1667. Newton became professor of mathematics in Cambridge in 1669. He lectured once a week on arithmetics, astronomy, geometry, optics, and other mathematics subjects. He was elected in the Royal Society in 1672. Leaving Cambridge in 1689, he became a member of Parliament until his death in 1699.
Newton is most notable for the creation of Newton's laws of motion. Newton's laws of motion are the three physical laws that form the basis for classical mechanics. They describe the relationship between the forces acting on a body and its motion due to those forces. They have been expressed in several different ways over nearly 3 centuries, and can be summarized as follows.
First, every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it.
The acceleration of a body is parallel and directly proportional to the net force, F, and inversely proportional to the mass. So, force equals mass times acceleration. Newton's third law states that for every action there is an equal and opposite reaction.
Newton's first law states that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. This law is usually recognized as Galileo's concept of inertia and is often coined as the law of inertia. You usually hear this law as an object at rest stays at rest while a body in motion stays in motion until an equal and opposite force is applied. Here's a great example of the first law using in everyday situations like cooking. In my hand there are 2 eggs, one raw and one hard-boiled. From where you are right there, you can't tell which one's which. But if you spin them on a hard surface, you can tell. How does that work, you ask? I'll tell you. A hard-boiled egg is essentially solid on the inside. Therefore, when you spin it and stop it, the egg will remain still. However, if you spin it and stop it, the raw egg, the egg will begin to spin again. Neat, right? Why does it do that, you ask? Well, when you spin a raw egg, the liquid, yolk, within the egg is spinning as well. And if you stop it from the outside, the shell, the yolk keeps spinning inside. It will make the egg start spinning again. Pretty neat, right? I thought so too. Hi, Sam.
As stated earlier, Newton's second law involves 3 different variables: force, mass, and acceleration. The law basically states that the net force on an object is equal to the object's mass multiplied by the object's acceleration. We actually see this every time we look at our weight on a scale. Although you may think that you are not accelerating, you actually have an acceleration downwards upon you of 9.8 meters per second. This acceleration is called gravity. This is why your weight is different than on Earth when you go to, say, the moon, for example. Another demonstration of this is pushing something heavy versus pushing something light. Since the heavier object has a higher mass, the net force acting upon it to move it must be higher than that required to move the light object. Those are just 2 examples of how this law can be used in everyday life, but there are many more. A third good example of how this can be used involves cars. Take 2 cars, for example, one more massive than the other. For the cars to accelerate at the same exact pace, the more massive car must have a greater net force acting upon it than the smaller car. That is Newton's second law. Newton's third law and final law of motion is essential to explaining why just about everything works the way it does. This law states for every action there is an equal and opposite reaction. So, for example, if I punch something,
Ow!
the force I exert on the object will be exerted back upon me. This is why it hurts when you punch things. Say, if I punch this brick, that hurt my hand. Another ordinary example of this force is walking. To walk, we exert a force on the ground, and it exerts the force back on us, making us able to lift our legs up and continue to move forward. So if Newton's third law was not existent, if I drop this egg on the ground, without the law, it would be in perfect condition because the force that it's putting on the ground would not go back into itself, so it would not break. Unfortunately, that isn't the case, and so when you drop an egg on the ground, it will crack. Although it can be very hard to think of things like that and how it works, it is entirely true. So likewise, when anyone is running, they're exerting a greater force on the ground, so the ground exerts a greater force on them, so that just allows you to run faster. Here are some more examples of Newton's laws. The force that Brian will feel depends on how fast I throw the basketball. So Newton's cradle is a good example of Newton's third law. Pretty much what it is, you lift one, well, it's a simple pendulum, well, 5 of them, and you lift one, and the force that that ball exerts on the second one moves it to the third one and the fourth one, and then the last one lifts up, and then it just continues, and it should be able to go forever, but air resistance stops that, and so it stops after a while.
Neat. When you stop a car abruptly, the car ceases to be in motion. However, the body within the car continues to be in motion. That means you can fly through the windshield. Therefore, it's always best to wear your seatbelt. To recapitulate on the first law, an object at rest stays at rest, like so, and an object at motion stays in motion until an outside force acts upon it, and in this case, it's friction.
So to recap for the second law, if I were to throw these at the same constant acceleration, the soccer ball should theoretically hurt worse or exert more force because it is more massive than the twig. Which one hurt worse? The ball. To recap on the third law, for every action there is an equal and opposite reaction. So, me jumping on the trampoline, it exerts a force back on me, causing me to bounce up and down. This is our friend Philip. Philip is a little confused. He has a couple questions.
If I dropped a cheeseburger and a hamburger, which one would exert the most force?
Excellent question there, Philip. Here, Tristan, why don't you take it away?
Well, the force exerted depends upon the mass of the two burgers. Whichever one has a greater mass will exert the greater force because force equals mass times acceleration, and they both have the same constant acceleration of 9.8 meters per second downwards. That acceleration is called gravity.
Does that mean it's the cheeseburger?
Yes.
It's the cheeseburger.
So does that mean if I drop this ping pong ball, it'll go forever?
Theoretically, yes, it should go forever, but due to air resistance and other imperfections and just our like standard environment, it would not be able to.
So does that mean if I just leave this tennis ball, it'll stay there forever?
Well, according to the first law, an object at rest stays at rest, and an object in motion stays in motion until an outside force is acted upon it. So, theoretically, yes it should, until something acts upon it. Like, I don't know, this table tilting or something.
So Philip, I hear you have one last question.
So since Newton didn't do anything exceptional in college, does that mean I can be like him?
No, get out.
Yeah.
The force that Brian will feel depends on how fast I throw the basketball. Newton's third law and final law of motion is essential for explaining just about... Oh crap, redo that. I was trying to save the wording and I couldn't.
Here is crap.
Second, the acceleration... typo.
Oh man.